2.4 billion years ago, oxygen-producing bacteria triggered a mass extinction that lasted 300 million years. The dawn of oxygen-producing bacteria marked a catastrophic turning point in Earth's history, but it's not just the presence of oxygen that was lethal, it was the way it reacted with other gases. Methane, a potent greenhouse gas, was prevalent in the atmosphere, and when oxygen came on the scene, it triggered a chemical reaction that released immense energy. This led to a devastating increase in atmospheric temperature, but also something far more sinister: a toxic soup that choked out the very life forms that had thrived in the oxygen-free environment, setting the stage for the mass extinction that would last 300 million years. The introduction of oxygen to the planet had a profound impact on the existing methane-rich environment. Methane, a potent greenhouse gas, was released from the Earth's crust and atmosphere through geological processes, and oxygen's reaction with methane triggered a catastrophic sequence of events. This reaction produced carbon dioxide and water, but also released heat, which in turn exacerbated the greenhouse effect. As the concentration of carbon dioxide increased, the Earth's temperature soared, leading to the collapse of the hydrosphere. Ice sheets began to form, and the planet descended into a prolonged snowball Earth ice age. This phenomenon, characterized by the nearly complete encasement of the planet in ice, would last for an astonishing 300 million years, effectively rendering much of the Earth inhospitable to life. The consequences of this reaction were far-reaching, with entire ecosystems being pushed to the brink of extinction. This pivotal moment in Earth's history would ultimately pave the way for the evolution of more complex life forms, capable of surviving in the face of extreme environmental conditions. As Earth's atmosphere continued to undergo a drastic transformation, life on our planet was forced to adapt at an unprecedented rate. One of the primary innovations that allowed species to survive this challenging era was the development of iron-based respiration. This process, which is still used by certain microorganisms today, enabled early organisms to bypass the oxidative stress caused by oxygen and instead harness the energy from iron-rich compounds. This adaptation not only provided a vital lifeline to early life, but also paved the way for the eventual evolution of more complex, oxygen-respiring organisms. Another significant evolutionary innovation that emerged during this period was the rise of anaerobic bacteria. These microorganisms were able to thrive in environments with little to no oxygen, exploiting the limited resources available to them. By doing so, they inadvertently created a vital food source for other, oxygen-based organisms that were beginning to emerge. The interplay between these anaerobic and aerobic ecosystems played a crucial role in shaping the trajectory of life on Earth, ultimately contributing to the complex relationships we see in modern ecosystems. One key takeaway from this turning point in Earth's history is the remarkable resilience of life, which, in the face of adversity, has consistently driven the adaptation and innovation necessary to ensure its survival. As we reflect on the Great Oxygen Uprising, it's striking to note that the events that unfolded over 2.4 billion years ago offer a haunting reminder of our planet's capacity for resilience in the face of catastrophic change. The mass extinction event brought about by oxygen-producing bacteria serves as a stark warning about the fragility of ecosystems and the unpredictable nature of environmental upheaval. In many ways, the Great Oxygen Uprising can be seen as a precursor to the modern-day struggles we face with climate change and the degradation of our planet's natural resources. The story of ancient life adapting to an oxygenated environment is a testament to the boundless potential for evolution and innovation that has defined the history of life on Earth. By drawing parallels between the past and present, we can learn valuable lessons about the importance of adaptability and resilience in the face of environmental adversity. This, in turn, can inform our own actions and decision-making as we navigate the complex challenges of our modern world. As we reflect on the Great Oxygen Uprising, it's clear that our planet's history is marked by both catastrophic upheaval and remarkable resilience. This pivotal moment teaches us that life can not only adapt but thrive in the face of adversity. With this newfound perspective, let's ask, what will be the next great challenge facing our Earth, and are we prepared to rise to it?